Okay, continuing our discussion on optimization, we have a problem to work on. We're to minimize a right circular cylinder that contains 20 cubic inches. So it's basically the Coke can problem. We have a circular cylinder, we need the volume to be 20 inches, and we want to minimize the surface area. Minimize the amount of material used to create this thing. So perhaps you're in a business that's producing some product, you're going to sell it, and if you can minimize the container, obviously that would cost less to manufacture. So let's put some dimensions on this. The radius of the circle and the height of the cylinder. Okay, so this is our shape. Now we were told the volume equals 20. But we either know or we can look up a formula for the volume of a cylinder. The volume of any cylinder is the area of the top or bottom times the height. So in this case, pi r squared times h. And this we know is 20. But that's not what we're trying to optimize. And if you recall from the previous video, the maximum or minimum points are going to occur either at endpoints, points where the derivative is 0, or possibly where the derivative is undefined. Unlikely to have an undefined derivative here. This is a real-world case. So what are we trying to minimize? Well, the surface area. The surface area consists of the two circles, top and bottom. So the surface area is going to equal 2 times the area of the circle, pi r squared, plus the area of the material we use to wrap around the side of the can. And that actually is a rectangle. If you were to cut this open and unfold it, we have a rectangle of height h and width the circumference of the circle. So h times 2 pi r. So you can see that if you were to unfold this, you would get a rectangle, the top and bottom of which are the circumferences of the circles, and the height is, of course, the same height. Okay, so we've got two equations. This is what typically happens in a real-world optimization problem. You end up with two equations. One you're trying to maximize or minimize, one that is fixed. And we know we want to take a derivative equal to 0. Well, naturally, we're not going to take a derivative where something is fixed. Nothing is changing. This is set to 20. What that's going to allow us to do is reduce a problem we have here. Surface area is a function of both r and h, two variables. And we're doing one variable calculus right now, so we can't really do this with two variables. So we need to eliminate a variable, and that's where this other equation comes in. If 20 equals pi r squared times h, I can solve for one of them. I'm going to pick h because it looks a little simpler to me. And h will equal 20 divided by pi r squared. So I've simply divided this part to the other side, and we've got h isolated. And that allows me to turn the surface area equation into an equation with just one variable. Put in what I now know h to be, right here. And we have surface area is just a function of r. Perfect. Now before we get carried away and do any derivatives, I want to simplify this equation a little bit. So this part doesn't simplify much. But over here we see a few things that we can do. 20 times 2 would be 40. I have a pi on the top and a pi on the bottom. So that will cancel. And I have an r on the top and an r squared on the bottom. So that will leave me r to the, on the bottom, or r to the negative 1, if I were to put it right here. So 40r to the negative 1 in reduced form. Now this is surface area. I'll just call it s, which is a function of r, radius. We should consider the endpoints. Well, we weren't really told anything too much about this, and the logical endpoints would be you can't make the radius smaller than 0. 0 is going to be kind of ridiculous. You're going to have a long string to infinity, probably not the best shipping container for our product. And r can only grow so much. Eventually the two circles themselves would use all the material, and we could find that number. But we once again see that that endpoint is going to be a pretty bad container. You're going to have a long, flat, two circles on top of each other, so not an optimal container. Let's see what happens when we take the derivative. So s prime of r squared, r is our variable, so this is the power rule. 2 comes out in front, and we get 4 pi r plus, and over here I have another power, r to the negative 1, so not plus, but rather minus 40 r to the negative 2. Okay, so there's our derivative. Now we take the derivative because one of our three sets of critical points is derivative equals 0. So I'm going to set this equal to 0. 4 pi r minus 40 r to the negative 2 equals 0. Let's just move one of them over, and I'll have 4 pi r equals 40 over r squared. Alternative method of writing that. Multiplying by r squared, I'm going to have 4 pi r cubed equals 40. And dividing by 4 pi, we'll have almost eliminated our r. R cubed equals 40 over 4 would be 10 divided by pi. And if we raise both sides of this to the 1/3 power, we've got our value for r. 10 over pi to the 1/3 power. And I don't have a calculator handy, trust that you do at home, and you can find a decimal approximation to r. From there, to find h will be quite simple, because we have r in terms of h in terms of r right here. So when you get a decimal for this, plug it in with appropriate parentheses to keep the denominator doing what it's supposed to do, and you'll have your value for h, and thus you'll have achieved your optimal container.